Hi, in this video we'll be going through the topic on memory. Okay, so what is the content we'll be covering? Firstly, we'll be looking at the different components of a process memory, such as text, data, BSS, heap, and stack. So we'll be looking at some code and trying to understand when we write a code and we compile it, which parts of the memory it goes to. And then we will look at another interesting topic, which is memory allocation. Okay, what are the different strategies that we can have in order to allocate and deallocate memory while the system is running. Okay, now let's look at the memory allocation from the top level view first. Now the first thing that we know is we have some code, okay, that runs on our system, and when we compile that code, basically it takes in the code that we've written plus any other libraries, and it creates a single binary file, okay, that will be stored, okay, within the memory. And since this size of the code is known beforehand, okay, we know the exact amount of space and we know the contents of the memory, so we are very clear of how much space our code occupies, okay, and what is in the code. And that is basically what we call the text segment, okay, of the memory. Okay, so the code is actually stored in the text segment of the memory. Now the next thing is global variables and static local variables. Okay, for global variables and static local variables, they exist for the entire program duration. So from the moment the system is powered up, okay, these variables will hold values, or can hold values that are needed for the entire duration where the system is powered up. Okay, and in this case, okay, we also know the amount of space that is required, okay, beforehand. Now this uh, goes into two different sections of the memory. Firstly, what you know is called the data section, okay, and the data section is basically where you have variables, okay, where the initialized value is known, okay. So there is, for example, integer x equals 97. So we, in the code itself, we specify initial value, okay. So in that case, variables like x will go into the data segment of the memory. How about variables or global variables or local static variables that are not initialized? So in this case, for example, integer x over here, this integer x will go into this segment called a BSS, okay, and BSS stands for block stated by symbol. And by default, what happens is all these uh, data variables stored in the BSS segment are initialized to 0. Okay, so this is actually a configurable option, usually in the linker script, okay, but we're not going to go to those details. But the default setting for most compilers and linkers is that the data that goes into the BSS segment will be initialized to 0. Okay, so if you have an initial value, it goes in the data segment. If not, it goes into the BSS segment. Then of course, while the program is running, you may need some dynamic memory. Okay, so memory that is allocated while the program is running. Okay, and I think most of us have used such techniques before in our C program. And basically what you use is malloc or free. Okay, so malloc and free. Malloc is to allocate the memory that you want, and free is to free it up, okay, once you've used it. Okay, and of course the important thing about this is the OS does not have any idea of the amount of space that you need or the contents that are going to be inside this. Okay, so it needs to be allocated to some portion of memory that has some room to grow. Okay, so it must be able to grow. So that is why if you notice the heap segment, at one end of the heap segment there is actually space for it to grow. Okay, and this is basically what we call the heap. The heap is where the dynamic memory in terms of malloc and free is used. Next is of course another common memory segment which we are familiar with, which is known as the stack. Okay, and the stack is generally used, okay, for temporary variables, okay, while the program is running. And when you say temporary variables, they are basically talking about local variables declared within a function, or function parameters. Okay, for function parameters, again, this is dependent on the processor architecture. Some processors may choose to, because of limited registers, they may choose to just push all your function parameters onto the stack. Okay, and then the function then pops it out from the stack. Okay, but for ARM, we know that in general we have 4 registers which are used for parameter passing, and anything beyond that 4 registers is what is pushed onto the stack. So different processors may have different ways of handling function parameters, but generally we do use the stack for such purposes. Okay, and of course, in terms of um, storing the return values, okay, in terms of the program counter or any return parameters, also we may use the stack. Okay, so of course, most of us may have in assembly language may have come across the push and pop terms. So push is wherever you want to push something onto the stack, and pop is wherever you want to take something out of the stack. Okay, and of course, the way the push and pop instructions work are also dependent on the architecture of the processor. Okay, so different processors may deal with it a bit differently, but the general idea is the same. So this slide here shows the sort of overview of the memory layout of how a system is. Okay, so we have the text segment, the data segment, okay, the BSS segment, the heap, and the stack. So these are the 5 main memory segments, okay, where uh, a code, okay, would occupy, okay, once you compile it and download it to the system. Okay, now let's have a bit more about the stack. Okay, so in this example we have a main function calling another function f. Okay, and of course you also notice that inside the main function you have 3 variables. F, you pass in 2 parameters, and there is also another local variable temp within f. Okay, so when I compile this code and I execute it, what happens? Okay, so the first thing is the main itself. As you can see, there are 3 variables a, b, and c, which will occupy the stack space. Okay, when the main function runs, when I call the f function, I need to pass in 2 parameters. Okay, so that is basically captured by x and y. So these are for the parameter passing, and I also have another local variable temp. Okay, so that is in f, and eventually I will um, finish f and I'll return. When I return, of course, those memory spaces are cleared up, and when I exit the main function, those memory spaces are also cleared up. Okay, so the thing about stack is as and when you exit from the function, okay, those variables will be popped out and effectively cleared from the stack. Okay, this is another example, okay, where we are looking at the different ways in which a code will be allocated to the various segments of the memory. Okay, so the first thing is of course the entire code. Okay, so the code here in this case, this function char f, and this function is the text. Okay, so that will be stored in the text segment of the memory space. Subsequently, we have a global variable string length, and we have a static local variable count. Okay, and this will be stored in the data segment over here. Okay, then we have our another global variable I size. Okay, in this case it is not initialized to any value, so it will be stored in the BSS segment over here. And then we have a malloc call over here. So for malloc, we will make use of the heap, okay, as we saw just now. And we also have a local variable char asterisk p, which will be stored on the stack space. Okay, so that gives you an idea of how the different sections of the code would occupy different segments of the memory system. Okay, so how about memory allocation and deallocation? Okay, when is memory allocated? So global variables and static variables are allocated the moment the program starts up. Okay, because all of these are known beforehand. For local variables, okay, whenever you call the function, then we will make use of the stack space to allocate memory for you. And dynamic memory is whenever you call the malloc function. Okay, and for all this memory is allocated, you must also deallocate it. Okay, so for global and static variables is basically when the whole program finishes. Okay, because they need to hold on to the values as long as the program is running. How about return function return? Okay, so sorry, for local variables where they are deallocated when you return from a function. Okay, like what we saw just now. When I call the f function, I allocated some variables, okay, onto the stack space. When I ended or when I returned from the f function, those memories were cleared up. Okay, so that is what you call the deallocation when you return from a function. And for dynamic memory is when you call the uh, free, and when you call the free. So malloc and free have to go in pairs. Okay, so that is basically an overview of the memory allocation and deallocation. Now let's look at example of how memory is allocated dynamically. So in this first instruction here, we are allocating, we are calling malloc 3. Okay, so in this case, we are asking for about 3 bytes of memory. And of course, we know that malloc, all malloc calls go directly to the heap memory space. So the first call allocates 3 bytes of memory. And subsequently, the next call P2 allocates 1 byte of memory, P2. And then we have P3 allocating another 4 bytes of memory. Okay, so in the fourth line of the code, what we do is we free P2. So this area here becomes available, okay, and free for use. And then in the next instruction, we allocate another 6 bytes of memory. And subsequently, we free P3, okay. And in this instruction here, we are allocating another 2 bytes. Okay, so what you saw here was, for this particular instruction here, when I wanted 2 bytes, I did not actually go here. I went here. I went back and saw where was the available space. Okay, so this is actually part of a strategy which we will discuss later. Okay, on where you should start looking for memory in order to allocate. Okay, whenever there is a need. Okay, so there are different strategies that are employed by the system. Okay, and we need to, or we will be exploring that shortly. Okay, so the last 3 lines are basically to free up the memory. So once I call free, all the memory that was allocated is now freed up. Okay, of course, as easy as it sounds, there are always cases where things can get quite messy if you do not use these techniques carefully and properly. Okay, so the first thing we're looking at is memory leaks that lose references to dynamic memory. Okay, so let's look at this situation here where I have a main function calling f. In f, I create a local variable. This is a local variable, correct? Okay, that means it's stored in the stack space. And after I create this local variable, I call malloc. Okay, that means now p has now pointing to a memory somewhere. Okay, so as far as the OS is concerned, this chunk of memory has already been allocated, okay, and assigned to this pointer p. And what I have done in this function is, instead of freeing up the memory, I return. So what happens? That means this chunk of memory has already been reserved for p, and since p did not free it, you will always assume that this memory is still being used. Okay, so the next time I call f again, so imagine that later on I call f one more time, I will create a new p, okay, and I will point to some other memory location which will be allocated to me, okay, because each time I call, it is a local variable, okay, on the stack. Okay, so that is a problem, correct? Because you are allocating memory but you're not freeing it up. Okay, so if I call f many times, after a while you will run out of heap memory, correct? Because you have allocated but you have not freed it up. Okay, so that is important thing to take note of. Okay, if you are allocating memory, you must make sure that once you have used it, you free it. Okay, so that the memory in the heap is freed up for some other process to use. Okay, another interesting issue here is what we call dangling pointers. It points to data that's not there anymore. Okay, so let's look at this situation here. Main calls of function f, and in f, what do? I create a local array. Okay, so in terms of memory, I have 8 bytes of memory, and p is starting address. Okay, p0 is basically the starting address of the first element. Now, p is basically the starting address of the first element in this array. So when I return p, I'm actually returning the address of where this array is starting. Okay, so and that return address is now pointed to by p. Okay, but what happens is, because p is allocated on the stack, the moment I return from this function, that means the moment I hit this curly braces, this p is considered no longer accessible. Okay, though it may still be there in the stack. Okay, it can very easily be overwritten by another function call or another use of the stack. Okay, so it is not guaranteed to be there anymore. Okay, so this is another dangerous use of pointers. Okay, in essence the wrong way. Okay, because you are trying to point to a address location. Okay, but that address location is no longer reserved for the array that was declared here. Okay, so these are again important aspects that we need to take note of. Okay, whenever we are dealing with memory references, we need to be very clear whether the memory, okay, that we are accessing is still valid and is still available. Okay, especially in situations where you are using them in the context of a function. Okay, and you want to access that memory resource outside of the function. Okay, so you need to be careful in such situations. Okay, so now we're going to look at a bit more into the memory allocation strategies that I mentioned earlier. So in essence, you can see here that if I have a 1 megabyte chunk of memory, okay, when I call malloc, what will malloc do? It will go in and try to allocate for me this 4096 bytes of memory. Okay, and once it successfully is able to allocate, it will return to me the address. So 8192 is the address. So this is, okay, the address here at this point is equals to 8192. So that is the starting address of where the 4096 bytes of memory is being reserved for this pointer variable here. Okay, so that is basically the job of malloc. Whenever you call malloc, you're supposed the OS is supposed to give you back, okay, this the memory that you requested, and it's supposed to give you back the address of where this memory is starting from. Now, of course, malloc is good. It's very useful because of the fact that we can do dynamic allocation while the program is running, but it leads to two issues. One is what we call external fragmentation or internal fragmentation. Okay, so what is external fragmentation? This is possible when we have various allocation sizes. Okay, so in that situation, you may have memory that remains unallocated. Okay, so if we look at the example in a while. The other one is internal fragmentation, where you have fixed allocation sizes and you have a situation where memory is allocated but is unused. Okay, so let's look at the following slides for a clearer example. Okay, so in this example here, we have external fragmentation, where you have a series of malloc and free. Okay, so in this first instruction here, we see that in this first 4 instructions, we are requesting for 100 chunks of memory. Okay, so that is what is happening: the first call, second call, third call, and fourth call. Okay, and after that, I am freeing up the second and fourth memory chunks. Okay, so when I call this free over here, free second and free fourth, I'm basically freeing up the memory that was allocated, okay, in those earlier instructions. Now, for the third, the last line over here, what do you see? I want to allocate, I'm calling malloc to allocate 200 bytes of memory, but it is unable to do it. Okay, but actually I have enough memory, correct? Because I have 150 here and I have another 100 over here. So I have 250 bytes of free memory, but only 150 are contiguous. That means they are in a one continuous chunk. Okay, and because of that, when I call for or the request for 200, it is unable to allocate this memory for me. Okay. Okay, so that was external fragmentation. So in external fragmentation, what you saw is I have the ability to allocate different sizes of data, and because of that, okay, when I want bigger data, I may not be able to get the continuous block that I want. Okay, so the other one is the other option is, why don't I allocate fixed bytes, fixed chunks of memory? Okay, so in this case, I assume that the fixed size is 100 bytes. Okay, so whenever I ask for memory, you always allocate to me in multiples of 100 bytes. Okay, so the first instruction is 90, so I will still allocate 100, but I use 90 and 10 is free. Okay, second, I wanted 120. Okay, so this is the first one, this is the second one, and 120, so the multiple will be 200. Okay, and so I use 120, but 80 is free. Okay, and the third one is I request for 10, so I allocate 100, but again only 10 is used, 90 is free. Okay, so you can see that a lot of memory has been allocated, but only a fraction of it has been used. Only 220 bytes have been used. So when I request for 50, okay, when I request for 50, when I have so much more, okay, available, it is unable to fulfill this request. Okay, so that is issue with internal fragmentation. Externally fragmented memory can be compacted, okay, which we will be seeing shortly. Okay, for fixed size allocation that we saw, it leads to internal fragmentation. Okay, but then there is less overhead to keep track of free memory. Okay, so what is this keeping track of all about? Okay, so let's see now. Now let's look at this example here where I need to keep track of available memory. Okay, so what I can do is I can keep double linked list or double linked list of free space, okay, to know exactly where is the next available free space going forward or going backwards. Okay, and what I can do is I can build the pointers directly into the holes, okay, because these are the currently available free spaces that I have. Okay, so in this case, for example, over at this address location 100, I can have a pointer that points to the next location 400. Okay, so that tells me that is the next available space of free space that is available, and similarly into 830. Okay, and of course I can also have another pointer that points backwards. Okay, so I can go in both directions, okay, to know the free space that I have, okay, uh, in the heap memory that is allocated. And of course, what we want is we want holes to be as large as possible. Okay, why? Because a larger hole can still satisfy a small memory request. Okay, but it's not true the other way around. Okay, and of course, we want fewer holes as possible so that we can as quickly as possible search for the available memory and allocate it to the process that needs it. And of course, when a memory is freed, what we want is we want to place that memory in a free list and adjust the next and previous pointers accordingly. Okay, and whenever possible, we do a merging, okay, to make the holes bigger so that we are able to cater to bigger memory chunk requests. Okay, so for example, here I have a free or I free up a memory chunk between two currently used slots. Okay, but since they're already used, I just free it up and call it a hole, but I don't merge it. In this case, I have a hole. Okay, originally I have a hole and then I do a free, so that means I can now merge with the hole before. Okay, the other way is I have a free space, I have a hole at the other end of the memory and I free up the current chunk in the middle, and then I can merge after that. And of course, if I have two holes and I free up the one that was originally occupied, then I can merge them together and create a very big hole to cater to even bigger memory requests. Okay, so let's see what it means to sort of deallocate memory. Okay, so if I were to deallocate the memory, okay, for example this chunk over here, what I would do is after that I would be able to readjust my previous pointers, okay, and as well as my next pointers, so that I am effectively merging and then I'm creating a free bigger memory chunk, okay, over here. Okay, so that is basically what happens when you deallocate memory and then you merge with the whole and the free space available. Okay, so what are some of the algorithms, okay, in terms of allocating memory? The first one is what we call a best fit algorithm, where we try to look for the smallest hole that can satisfy the request. So in this case, I'm looking for a memory chunk of 150 bytes, and then I go through. So initially I'll come here and then I'll come here and then I'll come here, and then I see that of all the three available spaces, this is the smallest one, okay, and then I'll allocate it over here. Okay, so of course I need to search the entire list every time, okay, and there is a possibility there can be a lot of very small holes, okay, that will eventually may not be effectively utilized. Okay, so for example, if I allocate 150 over here, then 150 would have been used, okay, but there will be still 50 that is unused, okay, and it may not actually be used for a very long period of time, because most memory requirements or most of the malloc uh, requests in the program may be bigger than that. Okay, so that is what we mean by having a tendency for more external fragmentation. The other option is worst fit, where I choose the biggest possible hole, okay, to allocate the memory. So again, in this case, I have 1,000, 2,000 and 200. So, and since I'm 150, I take the biggest hole, which is 2,000, and I allocate 150 out of that, okay, for this request. Okay, but and it still leads to fragmentation issues. In the first fit approach, basically what we do is we pick the first hole that is large enough, okay, to satisfy the request. So if I want a size of 150 bytes, okay, and if the first hole itself is able to fulfill the request, then I stick with it. Okay, so that is first fit, and the next fit is basically I start from exactly where I left off. So instead of going back to the beginning of the linked list, okay, if I started off over here, or this is the last place I stopped, then I check from this free space, okay, and then go on to the next free space and so on. Okay, so that is the next fit allocation algorithm. Okay, so in terms of compaction, what we can do is we can uh, deal with external fragmentation using compaction. Okay, for internal fragmentation, we can do paging or segmentation, which we will see in another class. Okay, for compaction, basically what we can do is this is basically what I have before, okay, and this is basically what you have after. Okay, and basically what you see is after compaction, all this free space that I had in between is now sort of combined together, okay, to create one big free space over here. Okay, so that is basically what compaction does. Okay, so the memory is still allocated, okay, and it is still used, okay, all these chunks of memory that I use. And only thing is you need to now reassign them to new address locations and move the data accordingly. So that is of course a major challenge. Okay, so because there's a lot of overhead involved to copy all the data and change all the pointer values. Okay, so and though it's possible, it's quite a tedious and time consuming process. Okay, but the idea is you want to just combine all the holes together, okay, to create one large hole. Okay, so there's also another way in which we can manage this. We can keep multiple lists of different hole sizes. Okay, and what we do is we take a list that closely matches our request. Okay, so I can have a list of memory chunks that point to chunks of 128 bytes or chunks that point to 16 bytes and so on. So when I want memory, okay, I look at the list that closely matches the request that I want, and I take the free space from that particular list. Okay, so that is also a good option, but it also leads to a lot of internal fragmentation. Okay, and how do you manage, okay, creating multiple free lists? Okay, so one way is you can start off with one single large hole. Okay, and then from there you keep on dividing the hole by 2 until the appropriate size memory is reached. Okay, so for example, if I want 3 megabytes of memory, okay, what I do is, and if I start off with 16 megabyte, I can split them into two separate lists. So one is 8 megabyte list and the other one is another 8 megabyte, and from this 8 megabyte I can split them up to another 4 megabyte, another 4 megabyte, and then from there I can allocate one, okay, to the 3 megabyte request that came in. Okay, so that is one way I can manage, okay, and create a multiple free list. Okay, so if I, for example, look at this scenario here where I am requesting a 100k allocation, okay, and the entire list is actually 1 megabyte. What I do is I split it first, okay, into half, okay, 512 512, and then split it again 256 256, okay, and then finally 128 128. Okay, so you can see that I keep dividing it by 2 until I reach the memory chunk that is just nice, okay, for the memory request that came in, and then from there I allocate one of these holes, okay, as the fulfillment of the request. Okay, and this leads to another extension which is called the buddy system. Okay, where in a free list I have buddies based on the memory chunks that are next to me, and with these buddies what I can do is I can split up from them, or I can compact them to create smaller or bigger chunks of memory. Okay, so what I need to do is, when I need to allocate memory, okay, I go up one level, take a hole and break it in two, okay, and these two holes are now buddies. Okay, so whenever I'm in allocation mode, I keep on breaking it, okay, and each time I break I have new buddies, and when the buddy size is just nice for the request, I give one of them, okay, to the user request. Okay, and once that the user request has been fulfilled and the memory has been used and the free is called, okay, then I can do a merging to move up, okay, the whole to the upper level. Okay, so let's look at example over here. So in this case I have a buddy system where again 1 megabyte and I want 100k. So what I need to do is I first split it up into 512 and 512, and from there I split it up into 256 256 and then 128 and 128. Out of the 128 over here I allocate this 100k. Okay, and if I have another request to say allocate 64k, what do? I can break up the 128k to another 64k 64k, and that chunk will now be allocated over here. How about if I request for 240k? Then I look for the closest memory, which is the 256k, and I allocate the 240k. So you can see that there's always some in some cases there will be memory that is unused, okay, because of the fixed size allocation based on the closest available size that matches the request. Okay, how about if I want a 256k? I can break up the other 512k into 256 256. Okay, so over here I break it up, okay, and then I allocate one. So when I free the 240k, what happens? I free it up, okay, and I get the full 256k back. Okay, and of course one thing you notice is here I do not do any merging, because the merging can only happen along the boundary of the upper level. Okay, so for 256 and 256 to merge 256k, I can only merge with another 256k and come up to 512k. Okay, so that is the merging rule. Okay, so when I free up the 256k over here, what happens is this gets freed, and this 256k and this 256k can then combine together to merge and create a 512k hole. Okay, so when it comes to merging, okay, we need to be careful to ensure that mergings are always aligned to the boundaries of the upper level. Okay, so you cannot just merge with the next available free space. It has to be aligned to the upper level. Okay, so that brings us to the end of this topic on process memory. Okay, so basically what we have learned is we have learned about the different types of memory uh, allocation rules in terms of the code, global variable, stack and heap and so on. And we also looked at a few different type of memory allocation techniques when it comes to dynamic allocation. Okay, so with this, I hope you have a good understanding of how memory is sort of utilized in our embedded systems, okay, and especially in the context of the OS. Okay, so thank you, and I'll see you soon.